The ocean covers over 70% of the Earth's surface, yet a significant portion remains unexplored. The sheer size and depth of the ocean make it difficult to study using traditional methods. The ocean environment is characterized by extreme conditions, including high pressure, low temperatures, and complete darkness at great depths. Human divers and traditional submersibles are limited in their ability to operate under these conditions. Autonomous underwater vehicles are designed to operate autonomously in harsh environments, making them invaluable for resource exploration and naval operations without risking human lives. They offer a cost-effective alternative for continuous, long-duration missions, quickly deploy to provide real-time data for emergency response, and help locate and monitor underwater resources for sustainable management. Additionally, their use in underwater surveillance and mine detection enhances maritime security. The mechanical design of our AUV encompasses various subassemblies, including 2 torpedoes launched from the AUV, specifically designed to function as self-propelled underwater explosive devices. Additionally, a gripper is utilized for retrieving underwater objects, supported by a marker dropper to enhance its operation. All sealed enclosures, such as those for the battery, cameras, kill switch, and DCVs, are engineered to prevent water ingress. Owing to the low-light conditions underwater, a torch is primarily used to aid the camera's vision. A 360-degree sonar sensor is employed for navigation and underwater acoustic imaging. The primary actuators of the AUV are its thrusters. The AUV frame features a cap-lock mechanism housing all the electrical systems within the hull. The frame is structured into 3 levels. The 3rd level contains the entire AUV manipulation kit along with the battery enclosure. These levels are interconnected using dovetail-type trusses. The 1st level houses the upper camera, kill switch, 2 hydraulic accumulators, and foam boards. The battery enclosure includes a charging port and 4 ventilators to enhance battery life and reliability. It is constructed from welded aluminum plates. The camera enclosure features an acrylic face for clear visibility and is constructed from Artelone material, utilizing 2 O-rings for radial sealing. The kill switch, on the other hand, is face-sealed with Artelone material and uses gaskets to aid in the sealing process. The DCV valve controls the pneumatic cylinder for torpedo launching. Similarly, its enclosure radial sealed for protection. The marker dropper is built from aluminum and acrylic materials and incorporates 2 solenoids that release 2 steel balls. After implementation, we faced a problem with sealing enclosures. First, the valve enclosure failed to seal during face sealing. Second, the camera enclosure also failed during face sealing. Finally, the battery enclosure had a design flaw in the vent brackets, causing it to fail to seal. A redesign took place to create new, efficient enclosures. Radial sealing was successful with the valve enclosure, preventing any water ingress. Similarly, the camera enclosure also passed the sealing test with radial sealing. The new design of the battery enclosure passed the sealing test, and the charging chamber was also efficiently sealed. The System Identification Node for AUV in our OS subscribes to IMU and fluid pressure sensor data, performs PID control for stabilizing 2-axis motion, and publishes wrench commands to control thrusters via our OS topics. For example, this trial demonstrates stabilization in the Y direction through pitch and yaw control. These graphs depict real-time sensor readings and control actions, highlighting the effective stabilization achieved in this scenario. This video demonstrates how to use keyboard inputs to direct the AUV for Warby Slam. The AUV adjusts its roll, pitch, and yaw angles, rotating accordingly. As depicted in the video, it begins moving along the x-axis in both positive and negative directions, exhibiting forward and backward movements while pressing on the right and left arrows of the keyboard. Additionally, the z-axis motion is controlled by pressing the up and down arrows on the keyboard, enabling upward and downward movement. The AUV keyboard teleop node is utilized in real-time testing of ORB SLAM, demonstrated by the generated path shown here.